Hello and welcome back to Quay Does Leetcode. Today I'm going to be doing problem number 74, search a 2D matrix. So for this problem, we're given a m by n integer matrix. And the matrix has the following properties. Integers in each row are sorted from left to right, and also, the first integer of each row is greater than the last integer of the previous row. So, so in this case, the 10 comes after is going to be greater than the 7. So it's actually a matrix where it is fully sorted. So all the rows are sorted, and then by the columns, it's also sorted because the first integer in each row is greater than the last integer that came before it in the previous row. So it is sorted. So given this matrix, we need to find an efficient algorithm that searches for a value. So we want to return true if the value exists in the matrix and return false if it doesn't. So for this example, we are given our target of 3, and you can see that 3 exists, so we return true. So the question is, how fast can we do this? Well, the brute force way of solving this problem, we could solve in O of m times n time, because we would loop through all of the rows, and for each row we would loop through the column and we would look for the answer. So we would have to loop through every single one, and so that would be a O of m times n. So could we do better than that? Well, we could, because we know that our rows are sorted. So our rows are sorted. So just think about, what if we were only searching one row? If we were just searching an array and this one row, and we wanted to find the 3, could we do that faster than an O of n? Yes, we could if we use a binary search algorithm. And if you don't know what binary search is, you can take a look at my other video where I go over just a simple binary search algorithm. And so if we do a binary search, you can imagine that we would do, if this is n, if we do a binary search, it'll take log n time. And if we have to search each column, if we have to search each row and do a binary search for each row, well then that's m times. So we would do this in O of m log n time. And that's faster than O of m times n, but could we do it even faster? Well, yes, we could. Finally, we could take advantage of the fact that we know that the first integer in each row is always going to be greater than the last integer of the previous row. So we could also do a binary search by the row to find out which row it we should even be looking in. So for example, if we're looking for the 3 and we're going to do binary search and we're going to start in this row. Okay, so we can look at the first value and the last value in the row. And if 3 is greater than the 3 is greater than or equal to the 10, or it's less than or equal to the 20, we know that it must be in this row here. But it's not. It's not in there. So, so now where should we look for it? Well, we know that the 20 is the greatest thing in this array. The 20 is the greatest thing. So our 3, and everything to the lower than the 20, all the rows lower than this row that we're on, all these numbers are going to be greater than 20. So we know that we can't find the answer here. We can't find the answer here, and we can't find the answer here. So we look and we see, is this the 10? Is our target less than the first thing in the row, and that's 10, and it is. So we know we should look up, and we should look for one row up, and that would be this row. And so now we found the correct row, because our 1 is, we have a 1 and a 7, and our 3 is going to be greater than or equal to our 1 and less than or equal to our 7. So we know that we've found our row. Now, so now we found our row, and all we have to do is do a binary search again on the row, and then we find this. So we can do this in O of log m plus log n time. And that's the fastest we can do this algorithm in. So that is the algorithm for solving this problem. So let's see it coded up. Before we move on, let's make sure we write our conditions that helped us do our binary search. So binary search for the row. Now, it was if our matrix at our row and it is the first thing in our row, so that's the first thing in the row is at column 0. If our target, let's stop that. If our target is greater than or equal to our matrix at our row and 0 at the 0 position, and target is less than or equal to matrix at row this position, which is -1, then we've found. Else if, so that is if we found the correct row. Else if our target is, so say our target is less than the matrix at our row and the 0 position. If it's less than, then we want to look above. So we're going to move our row to be, our we're going to have a, we're going to have a bottom pointer, and we're going to move our bottom pointer up 1. So it's going to be where our row is at, -1. And else if our target is greater than, then we want to move, greater than our matrix row at -1, which is this position. Then we want to move our top pointer, we want to move that down. We don't move that where our row is down. So that is, those conditions are going to help us write the code. So let's move on to seeing what the code looks like for this. All right, so the first thing that we need to do is we need to get our length of our matrix of our M and N. So we're going to make a rows, and that's going to be N is going to be equal to our matrix, our length of our matrix. And our columns, M, is going to be equal to the length of our matrix at our row 0, which is going to give us our first row, and we're going to get the length of that, which is going to give us how many columns we have. Then we're going to need to have our 2 pointers for doing our binary search of our rows. So we're going to have a top pointer, and that's going to start at 0, and then we're going to have a bottom pointer, and that's going to start at our rows N -1. So we're going to start our bottom pointer on our last row. So now we're going to loop while our bottom pointer is greater than or equal to our top pointer. So whenever our bottom pointer becomes less than our top pointer, then we're going to stop because we've gone through all of the rows that we could possibly go through. So now we're going to check if this is a case where we found the right row. Oh, and first we're going to need a variable that keeps track of if we found the row. So we're going to have a found row. We're going to set that to false. So now we're going to have a check to see if we've found the correct row. So remember, if our so first we're going to need which row we're on. So we're going to start the row in the middle row. So we need the mid row. So that's going to get, so the middle row is going to be row equal to our top plus our bottom minus our top divided by 2. And that's just a formula for getting the midpoint in an array. You could also do top plus bottom divided by 2, but if you do it this way, you prevent an overflow error. So we're going to do top plus bottom minus top divided by 2. And that's going to give us our mid row. Now we have our mid row. So we want to check if our answer is going to be in this row. So if our target is greater than or equal to our matrix at this row and the first thing, so if it's greater than or equal to it, then and the target is less than or equal to our matrix at this row and the last thing in the row, -1, then we know that the answer is somewhere in this row. So we found our row, and so we're going to do found row equals true, and then we're going to break out of this loop. So there's other conditions. The next condition is if our target is less than our matrix row at this row at 0. So if it's less than the smallest number, then we know that we need to move our bottom pointer, we need to move it to be lower. So we're going to move bottom, and that's going to be equal to row. So we're going to move our bottom pointer. We're going to move our bottom pointer up. We're going to move our bottom pointer to move it up. And then if our target is greater than our matrix row at this row and the last thing in the row, then we know that we need to be looking for it in a lower row. So we're going to increase our row. So we're going to move our top pointer, and we're going to do our at this row plus 1. Now, when we get through this loop, and if we haven't found the correct row, then that means that it can't be in any of the matrix at all. So we're going to say if not found row, we're going to return false. Or we could just return, if not found row, we're going to return false. Now we found the row that it's in. So now we need to find, we need to search through that row, do binary search through the row. So we're going to have another pointer called left, and we're going to have another pointer called right. Left is going to start at 0, and right is going to start at the last element in that row, which is going to be columns minus 1. Columns M, the length of the columns, minus 1. And now we're going to loop and we're going to do another binary search. So it's going to look pretty similar to our first binary search. So while our right pointer is greater than or equal to our left pointer, we're going to get our midpoint, and our midpoint is going to be our left pointer plus our right minus our left divided by 2. And then we're going to continue with binary search. So if our target is greater than our matrix at this row and at our mid, then we know that we need to increase our left pointer, and it's going to be mid plus 1. And else if our target is less than our matrix at this row at our mid, if the target is less than, then we need to look, we need to increase our, we need to decrease our right pointer. So it's going to be mid minus 1. And else, then we've actually found it, and so we can return true because we found it. And if we get through the whole thing and we haven't found it, then we're going to return false. And so that's the code for this problem. So let's run it and see what happens. So I misspelled matrix here, and now it's giving us the right answer. So let's submit. And we can see that it was accepted. So this is the correct answer. Again, this will run in log m plus log n time. Pretty efficient algorithm, just a double binary search. And yeah, so thanks for watching, and I'll see you in my next video.